yeah, so this work was also done with Luke Schaefer at MIT, and actually now we're both here at IQC. So any questions that you want to bother me with, you can also bother him with. Okay, so yeah, so this is going to be talking about using sort of a strange topic, using quantum linear optics to show hardness results for the permanent. I'm not going to assume any knowledge of quantum linear optics, so you don't have to know anything about that. Some basic quantum knowledge will be sort of useful, but hopefully I'll take things slow. And if you have questions, just put them in the chat, and I'll try to answer everything that I can. Okay, so let's get into it. So just want to start with like a brief review about the permanent. I'm sure most of you know this already. So the permanent is just an operation on squared matrices. So the permanent of a matrix A is the sum over all permutations sigma, where you take the product of all the terms AI sigma. So sort of the way I like to think about it is you have your square matrix, you take exactly one element from every row and column, you multiply them all together, and you sum up all of the possible ways of doing this. So for example, for a 2x2 matrix, it's just the product of the main diagonal plus the product of the off diagonal. For a 3x3 matrix, it's just these 6 possibilities. And the way that I sort of start to like to think about the permanent is by contrasting it with the determinant, right? So the determinant, superficially is very similar to the permanent. It only differs in its formula by this sign term, and yet the determinant has a lot of really nice properties. It's the volume of the parallelepiped spanned by the rows of the matrix equals to the product of the eigenvalues of the matrix. It's a homomorphism. It has an efficient polynomial time algorithm. In fact, even a sort of low depth algorithm. You can sort of just go on all day, sort of lauding the properties of the determinant, and yet you get to the permanent, and it has no easily describable geometric interpretation. It's not a homomorphism, and the best algorithms run in exponential time. So there's sort of a discrepancy here. And that's not to say that the permanent is sort of not a useful function to compute. In fact, we'll see later that in order to accurately predict certain physical systems, you actually need to compute the permanent. So it definitely does come up. And there's this sort of unpleasant thing where we can't seem to compute it more quickly. So, a natural question is, can you actually compute this thing faster? And, most of you probably have run into this before. The answer is probably not, due to a theorem by Valiant in 1979, which said that the permanent of a matrix is Sharpie hard to compute. So what do I exactly do I mean by Sharpie hard? So just as some review here. So this class Sharp-P, it's a complexity class, and it's a class of function problems of the form count or compute the number of accepting paths in some polytime non-deterministic Turing machine. So the sort of complete problems for this class would be, counting the number of solutions, or satisfying assignments to some 3-sat formula, or counting the number of inputs, which makes some polynomial size circuit evaluate to 1. And so that's what the class Sharp-P is. What do I mean by Sharp-P hardness? I simply mean that, if you had some oracle, I'm just going to call it per here. So you have some oracle for the permanent, you can just, ask this oracle to compute the permanent. If you had this capability, then any polynomial time machine with access to this oracle could compute any function in Sharp-P. I've written it here like you can query this oracle sort of as many times as you like, but in fact, in this talk and in much of the literature, you really only need to access this oracle once, and then there's just some sort of trivial post-processing that you do after that to compute some function that you want in Sharp-P. So what is sort of the consequence of Valiants reduction? Well, suppose that I hand you a 3-sat formula phi. Then using Valiants reduction, you can construct in polynomial time some matrix A such that the permanent of that matrix is exactly equal to the number of satisfying assignments to that 3-sat formula. So certainly, right, going back to this question, can I compute the permanent more quickly, right? Certainly, if I could count the number of solutions, then I could certainly tell if one exists, right? So if the permanent happened to be in polynomial time, then P would be equal to NP, because I could just be able to tell, is the number of solutions greater than 0? Great, this, I've shown that my three-stat formula has a solution, right? So, you know, it would be very unlikely that the permanent had a polynomial time solution. It's like, one of the things that complexity theorists really believe, right? You know, but maybe you came to me, it's like, I never believed that it had a polynomial time solution. You know, I thought that it had like, you know, a randomized algorithm with some access to some NP oracle, some like extremely powerful algorithm that can compute the permanent, right? But still, actually, you would get this sort of chain of inclusions here. And it's not exactly important what this chain is doing here, but sort of at the end of the day, you get that this polynomial hierarchy, this sort of what is conjectured to be an infinite sequence of complexity classes actually collapses to a finite sequence. And this is also an assumption that, you know, complexity theorists hold near and dear. So, you know, it's also probably not true that the permanent has even such a crazy algorithm like a BPP, the NP algorithm. So this is Valiants' theorem. And, you know, how would you actually go about, you know, proving a statement like this? Well, I said earlier that, you know, permanent, you know, doesn't have any good, so like easily describable geometric interpretation or anything like that. But that doesn't mean it doesn't have like sort of any good interpretations. In fact, it has some very good combinatorial ones. So I've just written out some adjacency matrix A here, and its corresponding graph on the left. And if you look at some non-zero term of this matrix, so a non-zero term of the permanent of this matrix rather, then if you look at the corresponding edges in the graph, it corresponds to what's known as a cycle cover. So it's just a collection of disjoint cycles that touches every vertex. And so you get this sort of nice interpretation that any cycle cover on the graph corresponds to a non-zero term in the permanent. And in fact, the permanent of this matrix is 2, so there are exactly 2 cycle covers in this graph. So this gives us some very nice sort of combinatorial interpretation of what the permanent is computing. So, you know, if A is an adjacency matrix, then the permanent of A is simply the number of cycle covers of the graph. But, you know, there's nothing special about adjacency matrix. You know, if I have a generic matrix, but I can just interpret it as a matrix that's an adjacency matrix with edge weights, right? And so then the permanent of A is simply the sum of sort of the weighted cycle covers of the graph, where you take all the product of all the edges on the weights. So this is sort of exactly the sort of intuition that Valiant uses to show his Sharpe hardness reduction. So what he does is he starts with a 3-sat formula, and then he builds some graph by sort of smashing these gadgets together, where the number of cycle covers on the graph exactly corresponds to the number of solutions to the 3-sat formula. So roughly speaking, every cycle cover of the graph corresponds to some solution. And then, because he's counting cycle covers, he knows that there's some underlying matrix, you know, sort of governing this whole thing. And if you were to take the permanent of that matrix, you would count the number of cycle covers, and therefore you'd be counting the number of solutions to a 3-sat formula, and therefore you'd be solving a Sharpe hard problem. So it must be the case that, you know, calculating the permanent is Sharpe hard. So for the purposes of this talk, you know, how do we sort of go beyond what Valiant has done here? So sort of the overarching goal is sort of to determine sort of what the landscape of permanent hardness is. Like, are there different classes of matrices for which the permanent is easy, or are there, you know, or is it just the case that, you know, basically you pick any class of matrices and it's just hard to compute the permanent of those types of matrices? Yeah, and, you know, even already sort of Valiant's work did a lot of work here, right? So his proof already extends to non-negative or even 0-1 valued matrices. So even if I just give you a 0-1 valued matrix, like an adjacency matrix, you know, calculating the permanent of that matrix is Sharpe hard to do exactly. But I wanna make an argument that his proof technique doesn't work well for certain other types of matrices. In particular, matrices that have some sort of matrix group structure. So like the invertible matrices or the unitary matrices. So it turns out that the matrices that sort of turn up in Valiants reduction are probably invertible, but this would be like really tedious to prove, and it seems like, you know, it's more accidental than intentional, if anything. But if you ask for something stronger, like, you know, are his matrices unitary? Well, the matrices that come up in the reduction definitely are not unitary, and there's sort of no obvious way forward here. Sort of the intuition is that, you know, you're dealing with these sort of local graph gadgets, and you're kind of stitching these together, and then at the end of the day, you're supposed to impose some sort of global graph, like, you know, global structure on the matrix, and that just seems very, very difficult to do. So there's sort of no obvious way to go forward here. So we need sort of a new plan. And our plan is going to be to use a theorem of Scott Aaronson in 2011, which showed that the permanent is sharply hard to compute. All right, so obviously this is a bit of a joke. This is the same theorem that Valiant proved in '79. So what took Scott so long? Well, the reason that that this is even a thing is that Scott's proof is entirely quantum. So what it does is it sort of removes all of this sort of difficulty of these graph gadgets and stitching them together and sort of figuring out what these things do. And it sort of offloads all of that difficulty onto some sort of well-known theorems in linear optics. So the upshot of that is, like, if you're a physicist or you know these theorems, then the Sharpe hardness of the permanent sort of now becomes sort of like a one-liner. It's just like an extremely beautiful proof if you know these things. But sort of the question still sort of remained, like, he wasn't really able to show anything that wasn't already known. He was just sort of reproving things in some of this like sort of extremely novel way. And the sort of the purpose of this talk is to show that actually, yes, you can take his results and sort of extend them in a natural way to get hardness for new classes of matrices that we didn't know before. So here are the results. Here's sort of like the headliner result. So if you have a matrix A and it's sort of any of these classical Lie groups over the complex numbers, then it's still sharply hard to compute its permanent. So for instance, the general linear group, the invertible matrices, the orthogonal matrices, the unitary matrices, and even the symplectic matrices, all of these matrices are still hard to compute the permanent of. And sort of for the purposes of this talk, I'm going to be trying to show and outline the proof of the unitary case. But before I do that, I want to mention that that these theorems over the complex numbers can actually be extended to theorems about finite fields, which is kind of interesting. So let P be some prime characteristic not equal to 2 or 3. Then there exists a finite field of that characteristic such that computing the permanent of an orthogonal matrix over that field is hard for this class mod PP. Now, so I may have not seen this class before, but it's sort of the direct analog of Sharpe P except mod P. So for instance, the complete problem for Sharpe P is count the number of solutions to some three-sat formula, whereas the complete problem for mod PP would be count the number of solutions to a three-sat formula mod P, mod this prime. And it's still believed that this class is hard to compute. For instance, by Toda's theorem, like if you had a polynomial time algorithm for problems in mod PP, then once again, the polynomial hierarchy would collapse. So this is still thought to be a sort of computationally intractable class. But there's a couple unsatisfying things about this theorem. One of the things that you might think is sort of unsatisfying is, we haven't proved the theorem for P equals 2 or 3. So what's going on there? Well, what's going on there is that you're actually obstructed by tractability. So for P equals 2, right? So where fields of characteristic 2, -1 is equal to 1. And we saw that earlier, like the determinant only differed from the permanent in this sign term. So now the sign term goes away. So any algorithm that you had for the determinant also works for the permanent because these quantities are exactly the same. So of course we have efficient algorithms for determinant. So we also have efficient algorithms for the permanent in fields of characteristic 2. Now for P equals 3, the case is like sort of even more interesting. There happens to be a non-trivial algorithm due to Kogan in '96, which showed that for orthogonal matrices, computing the permanent of an orthogonal matrix over a field of characteristic 3 is actually in polynomial time. So this is just some sort of kind of crazy off-the-wall theorem. And it's kind of strange that this work would shed light on this fact, but this work sort of for the first time showed why Kogan wasn't able to extend his arguments to sort of P equals 5, P equals 7. People, keep going because he's running into this wall of intractability. So it explains for the first time what's really going on here. But sort of the other thing that sort of might be unpleasant about this theorem is that we're working over this field fp to the 4, which is like sort of an unnatural field to be wanting to calculate the permanent of an orthogonal matrix over. So you might want to just work over fp, and we can say a little bit there as well. So the permanent of an orthogonal matrix over the field fp is mod pp hard for about a limiting density of like 1/16 of all primes. So those are the main results of this work, and I'm going to try to sketch the proof of the unitary case if there's any questions about anything, the results, maybe this is a good time to pause and like reflect.
Yeah, I have a question.
Yeah.
So where does that 1/16 come from? Is it from some congruence condition, or is it more complicated?
Well, it comes from the fact that you need a certain like root to exist. Like we're at the end of the day, we're gonna apply like Chebyshev density theorem to some
Sure.
to something, and yeah.
So is it that you know that there's some density, or you can only show it for such a density of primes? Like, do you have a converse?
No. Oh, sorry. Yeah, that's a good question. I conjecture that this should be true for everything not equal to like 2 or 3. There's some reason to believe that our techniques will not extend, will not give you this. That there's some obstruction in our technique to give you more things. Like it's not just like something that's going wrong in our analysis is loose or something like that.
Mm-hmm.
But if I had to put money on it, I would say this statement should be true for basically all primes.
Okay, maybe one last question. So what about degree 2 and 3? Do you know what's happening in between there? Or is that still open?
Yeah, so like for degree 2, I think you get some like 3/16 of all primes or something like this.
Interesting. Cool, thank you.
Yeah.
Hey, Daniel, can I ask a quick question?
Sure, David.
So for p equals 2, you say the permanent is the determinant, so you can compute it by linear algebra. Is there some idea of cogons that can be explained in sort of a phrase that would give us an idea of how it works? I mean, is it linear algebra or is it something else for p equals 3?
Yeah, it's I forget the exact the reason why it's very specific to the fact that like -1 equals something that you want it to be in fields of characteristic 3. It's been a long time since I've looked at the proof. I don't really remember at this point, but it's fairly magical. Like I read the proof and like tried to like have some like big takeaway message from it, and I didn't really extract one.
Okay, thanks. I think there's another question from Peter Nelson.
Yeah, so the if p to the 4, does that still work if you change the 4 to a 5?
Yeah, I think that should be fine.
Okay.
I'm okay. Maybe I'm a little bit unclear about that. It should probably be fine, but then maybe don't hold me to that.
Okay.
Okay, cool. So if there are any other questions, I'm going to go on. But if it just took you a long time to type your question, just feel free to interrupt me. It's fine. Okay. So I'm going to start by outlining what Scott Aronson did for his proof, and then I'll show you sort of how to modify it to get the things that we want. So sort of the overall structure of his proof is he's going to start with some poly-size circuit C, and he's going to want to count the number of satisfying assignments or the number of solutions which make that circuit evaluate to 1. This is sort of a canonical Sharp-yard problem. For some sort of technical reasons, actually we're going to be calculating this quantity delta C, which is the number of unsatisfying assignments minus the number of satisfying assignments. But clearly, like if you could calculate delta C, then you could calculate the number of satisfying assignments and you'd be fine. So sort of the goal is we're going to start with this and we're going to encode delta C into some permanent. And it's going to go in 3 steps. So the first step is going to be to encode this quantity delta C into the transition amplitude of some quantum circuit over qubits. So you start in the all-0 state, you apply your quantum circuit Q, and you look at the resulting amplitude on the all-0 state, and this is going to be proportional to this quantity delta C. Then we're going to take our quantum circuit Q over qubits, and we're going to convert it into a linear optical network L. And so the transition amplitude in this linear optical network is going to sort of be proportional to the transition amplitude of your sort of quantum circuit. And we'll get into what exactly that means later, but for right now, just sort of take it on faith. And then finally, in the third step, we're just going to use like a well-known correspondence between transition amplitudes and linear optical networks and the permanent. So this transition amplitude in linear optical network is going to be proportional to the permanent of some matrix. And so if you can calculate the permanent of this matrix, you can sort of work your way back through these proportionalities to calculate this quantity delta C. which will have shown that, calculating the permanent of a matrix is sharply hard to compute. So that's what we're going for. That's like the overall goal. And our contribution sort of comes between steps 1 and 2, where we need to be a little bit more careful about how we're converting our quantum circuit into this linear optical network. And we'll get into that more later. Okay, so how do we do this step 1? I'm actually not going to spend a whole lot of time here because it's sort of a standard trick, but we want to, just to recap what we want to do here, we want to create some quantum circuit Q such that if you look at the transition amplitude going from the all zero state to the all zero state, it's exactly equal to delta C over 2 to the n. And there's sort of 2 perspectives that you can take, or there's probably many perspectives. There's sort of 2 perspectives that I'm going to show you here. One is simply just like a quantum circuit perspective. If you're sort of used to dealing with quantum circuits, you can just sort of prepare the equal superposition of all inputs, apply your circuit to this equal superposition, and then apply Hadamard's again. You can sort of just do this calculation and see that you get this quantity delta C over 2 to the n after you've done the calculation. Sort of a shortcut or something that you may sort of hold on to as something that you might want to believe and that will help you get there is sort of like a Boolean Fourier perspective. So, it turns out that this quantity that we want to compute, this delta C over 2 to the n, is exactly the Fourier coefficient of C at the empty set. And then, so now that you know that, you can just sort of like appeal to the fact that quantum computers should be good at doing Fourier transforms and just sort of believe that you can sort of construct such a circuit which is going to have this behavior. So that's actually all I'm going to say about this first step. So after this step, we will have constructed this quantum circuit Q such that if we start in the L0 state and end in the L0 state, we're going to get this quantity delta C over 2 to the n. Okay, so that was the first step of our proof. And of course, now to do the second step and the second and third step, I need to tell you what linear optics, what is linear optics even. So that's going to require sort of like a bit of a digression, a long digression, but hopefully we'll get there. Okay, so I'm going to start with an abstract sort of definition of what this is, and then I'm going to move to sort of a more physical definition of what a linear optical network actually is. So abstractly, I'm just going to describe it to you in contrast with quantum computing over qubits, so m-level systems. So the states in normal quantum computing is you have n-fold tensor products of Cm, right? So you have n-fold tensor products of a state that has m levels. When you're doing linear optics with photons, because photons in nature are indistinguishable, you have to have some way of symmetrizing this expression. So your states are actually n-fold symmetric tensor products of Cm. So you're sort of averaging over all permutations of the tensor product. And your operations in normal quantum computing are m to the n by m to the n unitary matrices, whereas the operations that you have in linear optics is you take a single unitary which acts only on sort of one subsystem on a single photon with m layers, and then you apply its sort of n-fold tensor product. So you apply the exact same transformation to all your photons. So that's sort of a very abstract definition of what's going on, but it sort of helped me to think about this when I was first thinking about these things. So maybe it might help you as well. I'm going to give sort of a completely different like physical interpretation of what linear optics is, which is sort of easier to work with in a lot of cases. Okay, so I'm going to first.
Danny, I have a question.
Sure.
Like, what do I have the power of universal quantum computation with linear optics?
Okay, that's a great question. We're going to get to that in a second. Okay,
no worries.
Morally, yes and no. I'll explain a little bit of it in a bit. So the states are what I like to think of as sort of like a quantum analog to sort of the classical balls and bins model. So you have the possible locations where a photon can be, these bins that are called modes in the parlance of linear optics, and you have photons which can sort of reside in these modes, and they can sort of be in whichever sort of configuration you like. But these photons are sort of indistinguishable. So there's no sense in which in this configuration here, there's like like the first photon is on the bottom and the third photon is on the top or anything like that. There's just 3 photons all in that mode. So those are what the states look like. Just notationally to describe these states, I'm going to introduce this notation. So ket S1 up to Sm is just a state that has S1 photons in the first mode, S2 photons in the second mode, and so on. So, these are, legit quantum states. So we can have superposition. So I can have a superposition of, 1 photon in the first 3 modes, and the state which has 2 photons in the second mode and 1 photon in the third mode. And for the purposes of this talk in linear optics in general, you usually have like the number of photons is conserved. So you always have the exact same number of photons and modes and all photons, like as if you sum up over all your modes. Okay, so those are what the states look like. So what do the transformations look like? Well, we saw earlier in this sort of abstract definition that we were sort of taking n-fold tensor products of the operation that we wanted to apply. And this is just sort of going to sort of give you a sense of what that looks like on these symmetrized states. So the idea is we're going to have a single unitary, which is specified by its action on 1 photon, and then we're going to sort of lift it via some homomorphism to like the entire space of all photons. So I'll give you an example of what that looks like. So here's a state that has 2 modes. There's only 2 basis states, right? There's the state that has 1 photon in the first mode, and there's the state that has 1 photon in the second mode. All right, so these are our 2 basis states. And we're going to apply this transformation L. This happens to be the Hadamard transformation to these basis states, and let's just sort of see what happens, right? So if we were to apply this transformation L to the state that had 1 photon in the first mode and 0 photons in the second mode, then you just do this sort of like standard thing you do in quantum computing. You take your matrix, you multiply it by the state vector, and you sort of write it back out and show your ket notation. So now we have a uniform superposition that has one state that has 1 photon in the first mode and another state that has 1 photon in the second mode. All right, and a similar thing would happen if you were to apply this transformation to the state that had 1 photon in the second mode, except now so you pick up this minus phase. So sort of the interesting thing happens when you start applying these transformations to states that have more than 1 photon in them. So imagine we take the same transformation L and we have the same number of modes, but now we have more than 1 photon. So now we have 2 photons. So now we need to do some accounting here. So let's sort of do it sort of one at a time. So let's first look at the amplitude that you might have on the state that has 2 photons in the first mode and 0 photons in the second mode. Well, if we go back to our calculation over here, the sort of amplitude that you have of having the first photon go to the first mode is 1 over square root 2. And the amplitude that you would have to have the second photon go to the first mode is also 1 over square root 2. So the sort of amplitude that you get on this state is 1/2. Right? Similarly, for the case where we have 2 photons in the second mode, right? Both photons have to go to the second mode. So we have 1 over square root 2 coming from the first mode, and we have minus 1 over square root 2 coming from the second mode. Right now, the interesting thing happens when we look at the state that, like, what is the amplitude on the state that has 1 photon in each mode? Well, in this case, there's sort of 2 possibilities now, right? There's a possibility where each photon goes to its respective mode. So the photon in the first mode goes to the first mode, the photons in the second mode goes to the second mode, or they can now swap, right? So the first mode can now go to the second mode and vice versa, right? So if you do that calculation, you see that you get a contribution of 1 over square root 2 and 1 over square root 2. But in the second case, you get a contribution of 1 over square root 2 and a contribution of 1 over minus square root 2. And when you sum these together, you get a contribution of 0. So the upshot of this calculation is that the final state that you get after normalization is actually this sort of strange entangled state. Either both of the photons appear together in the first mode, or both of the photons appear together in the second mode, but they're never apart. So they're sort of like entangled now, which is kind of strange because it seems like we applied the same transformation to both photons, and yet somehow now they're coming out entangled. And this is exactly due to the fact that these photons sort of interfere with each other because they're indistinguishable. All right, and this effect is known as the Hangel-Mandel dip, which sort of expresses this fact that photons tend to bunch together in these experiments. They tend to clump together in these modes. Okay, so that's sort of one example of how you might lift a transformation to more photons. So the general transformation is described by this phi transition formula. So imagine that I have a state that has m many modes, and I want to apply some linear optical transformation to that state. So I'm going to apply a unitary, which an m by m unitary to the state, but it's going to be lifted by this formula phi here. So if I start in the state S and I apply my linear optical network and I look at the resulting amplitude on the state T, this amplitude is equal to the permanent of some matrix divided by some normalization constant, which is not so important for us. So what is this matrix LST? Well, it's simply the matrix that you get by taking SI copies of rho I from L and TI copies from column I from L. So this sort of expresses the fact that if you have more than one photon in a particular mode, you're going to need to take the corresponding row or column in the matrix more than one time to sort of account for that fact. So let's go back to our example again to see this sort of formula in practice. So here's the same example, except now I've sort of color coded the entries of the matrix. So this is the operation we want to apply. If we start in the state that we started before earlier with one photon in each mode, we wanted to look at the amplitude on the state that had 2 photons in the second mode and 2 photons in the first mode and 0 photons in the second mode. Then this matrix LST is the matrix that we get by taking the first column twice. So now we have the first column twice, and the permanent of this matrix LST is 1. And so then after normalization, we see that this transition amplitude in the linear optical network is 1 over square root 2, which is exactly what we derived on the previous slide. And so a sort of silly observation that I want to, is sort of like, in some sense, like the big takeaway of this talk, is that if you look at this formula and you set the starting state to be 1 photon in every mode and the ending state to be 1 photon in every mode, then this transition amplitude is exactly the permanent of the matrix L, because we're taking 1 copy of every row, 1 copy of every column, which is exactly L itself. And so now we have the permanent of L itself equal to some transition amplitude. And since L is unitary, we're sort of cooking with gas in some sense. We're kind of close to what we want. So going back to our proof outline again, we saw in step 1 how to encode this Sharpie-hard quantity delta C into the transition amplitude of this quantum circuit Q. And then we just saw that if you happen to already have a linear optical network, then the transition amplitudes in that linear optical network are expressed by permanence. And so now we just sort of need this glue. Like, how do we take the quantum circuit Q and convert it into a linear optical network L? And this goes back to the question earlier, like, can linear optics actually even simulate what's going on in our quantum circuit? And the answer is yes, in some sense. So it comes down to this famous theorem in linear optics called the Canil-Laflamme-Milburn theorem, which at least one form of the theorem states that post-selected linear optical circuits are universal for quantum computation. So what that means, sort of formally, is that if I hand you some quantum circuit Q, and let's say it has a polynomially many C sign and single qubit gates. In case you haven't seen the C sign gate before, it's just a simple quantum gate that applies a phase if both of the inputs are 1. And it's known that this C sign gate is universal. So if you have C sign and as many single qubit gates as you want, you can do anything in quantum computation that you'd like. So we haven't really restricted the gate set at all. We're just looking at this particular gate set. So if you're given a circuit that's comprised of these gates, you can actually convert it efficiently into a linear optical circuit that has polynomially many modes, such that if you look at the transition amplitude, a particular transition amplitude in this linear optical network, it's exactly equal to the transition amplitude that you want in the quantum circuit. Albeit it's sort of attenuated by this factor of 1 over gamma, where gamma is the number of C sign gates that appears in your circuit. Okay, but there's sort of one thing that's sort of unsatisfying about this, which is that your sort of starting and ending state for your linear optical network is this state where you have 1 photon in every other mode. And we'll see where that comes up later, and we'll see where that comes up later and how it affects the proof. But sort of equipped with this theorem, we actually now have the entirety of the Scott-Aronson proof of the Sharpe hardness of the permanent. So once again, we start with the fact that we can encode delta C over 2 to the n into the transition amplitude of this quantum circuit Q. Now we just sort of directly apply the KLM theorem here so that the transition amplitude of this quantum circuit is equal to the transition amplitude of this linear optical network. And then we just use the correspondence that you saw a couple of slides ago, and we know that this transition amplitude is equal to the permanent of this matrix LII. And now you really see why this starting and ending state in the Canilla-Flum-Milburn theorem is sort of undesirable for our purposes, because this matrix L sub I, L is a unitary matrix, but L sub I is a submatrix of a unitary matrix, and a submatrix of a unitary matrix need not be unitary. And so we sort of destroyed the sort of quantumness of our matrix. And so we only get that the matrix, that computing the permanent of a generic matrix is Sharpe hard rather than the unitary matrix, the thing that we really wanted to show. So we're going to need to sort of circumvent this somehow. And in order to do that, I'm going to need to talk a little bit about what the KLM theorem is actually doing. So sort of the first major bottleneck in the KLM theorem is how do you even represent a qubit in a linear optical network? And you sort of run into this problem immediately where a qubit is either in the state 0 or 1, but the number of photons in a linear optical experiment is always conserved. So it's not like I can just have a single mode corresponding to a single qubit and just remove that photon whenever I want and put it back in where I want, because this qubit has to be preserved, or the number of photons has to be conserved. And the solution here is a pretty generic one that you've probably seen before, which is to use 2 photons and 2 modes and 1 photon to encode a single qubit. So this is called it's known as the dual rail encoding. So what I've drawn here on the left are the qubits, and on the right are sort of the encoded states in linear optics, right? So the qubit 0 is represented by the state that it has exactly 1 photon in the second mode, and the qubit 1 corresponds to the state that has 1 photon in the first mode but no photons in the second mode, right? So you can sort of see here where like a NOT gate applied to the qubits kind of corresponds to a swap gate in the linear optical network. And this is exactly the source of this 0, 1, 0, 1, 0, 1 that we saw in the statement of the Canilla-Flum and Milburn theorem, this KLM theorem, and is exactly the source of non-unitarity that's coming up in Aronson's proof. So somehow we're going to have to sort of circumvent this problem. So in order to sort of talk about the solution to this problem, I'm also going to want to talk about how KLM does the sort of entire reduction. So how do we just showed how they represented states, but how do they actually do transformations as well? Well, the hope that you might have is that your quantum circuit is comprised of these small unitary gates. Maybe you can just take those small unitary gates and apply them directly to these dual rail encoded qubits, and it just works, right? So hope is just to take each gate in the quantum circuit and apply directly to these dual rail encoded photons. And in fact, for the single qubit gates, this just works, right? So the transformation that you want to enforce on the qubits is also the same if you were to apply the same unitary to these encoded modes. And this has to do with the fact that sort of at this small dimension, these Hilbert spaces are actually isomorphic. But for simulating a C-sign gate, things get a little more complicated. So just to jog your memory, right, the C-sign gate is the gate that applies a phase exactly when both of the input bits are 1. Otherwise, the gate just does nothing, right? So one sort of trick that we can use right from the start is we only ever really need to look at the first mode of a dual rail encoded qubit, right? Because if there happens to be 0 photons in that mode, then we know that the corresponding qubit was in the state 0. If there's 1 photon in that mode, we know that the corresponding qubit was in the state 1. So what we can do is we can sort of search for some 2-mode gate L such that all of the following conditions hold, right? Like if you start with 0 and 0, so this would be like the first mode of the first qubit. This is like first mode of the second qubit. If both of these are 0, then your transformation just does nothing. It just does nothing. Same thing if there's exactly 1 photon in one of these modes. But if there are 2 photons in one of these modes, then you need to apply a phase of -1, right? So you can it's like totally reasonable to hope that such a gate exists, but actually such a gate does not exist. So you just can search forever for this gate and you won't find it. So some sort of extra resource is necessary here. And in the KLM theorem that I stated earlier, the extra resource was post-selection, and I haven't yet mentioned that, so something's got to give there. So we're going to use post-selection to solve this problem. So instead of starting with just the dual rail encoded qubits, I'm also going to impose that I'm going to add some extra modes, which are just going to be used for post-selection. So every state that we consider is going to start with 0 photons in the 3rd mode and 1 photon in the 4th mode. And every state we consider at the end is also guaranteed to have 0 photons in the 3rd mode and 1 photon in the 4th mode. So this is the post-selection. We're only going to look at states of this form. And then when you look at states of this form, you actually see that such a C-sign gate does exist. And you get that this sort of attenuated by this factor 1/4, just like we see in the statement of KLM. So just here, these are just some examples, right? Like if you have 0 and 1, the C-sign gate shouldn't do anything, so we have 1/4. If it's 1 and 1, then the C-sign gate should spit out the same state except with a minus sign, which you see here. And now you also have to check for some sort of weird edge cases as well. Like if you have 1 and 1, you don't want the circuit to sort of dump all of the photons into the 1st mode, because then you're sort of violating the fact that you had the dual rail encoding to begin with. So you also have to check to make sure that conditions such as these hold. But you can check those, and you can find that such a gate L does exist, and so you can apply C-sign gate. So now we've sort of shown that under post-selection, we can apply any gate in the circle we want, and that's what gives the KLM theorem. So how do we sort of take something like this, and there's like a lot of constraints going on here. How do we take something like this and sort of modify it for our needs? Because it's like already sort of like a very well-tuned theorem, and it seems like it might be sort of difficult to get to where we want to go. So just to remind you what our goal is, right? We started with this quantum circuit where the transition amplitude of that quantum circuit is something we want to compute, and we want to construct some linear optical network L where that transition amplitude is proportional to the transition amplitude of the linear optical network, except we need to start in the state that has 1 photon in every single mode and ends with 1 photon in every single mode, which sort of violates this dual rail encoding that we saw earlier. And so this problem is that how do we get around this dual rail encoding? And the solution is sort of simple conceptually in retrospect. It's just prepare the dual rail encoding in advance using sort of yet another gadget. So the solution looks something like this. So just to recall, like the KLM solution used 2 modes and 1 photon to represent a single qubit, whereas our solution is going to use 4 photons and 4 modes to represent a single qubit. So here's what an encoded qubit would look like. It's just 4 photons and 4 modes. And before we do anything, what we're going to do is we're going to apply some sort of encoding gadget to our encoded qubit. And what that's going to do is it's going to take the photon in the 1st mode and sort of dump it into this 3rd mode here, right? So now, if you look at the resulting first 2 modes, they're now in this dual rail encoded state. But once again, the problem is that such a transformation doesn't exist. And so we need to use yet another round of post-selection, which is why this 4th mode exists. So this 4th mode exists so that we can use this mode to post-select the fact that this encoding gadget is going to work. But after we've done this post-selection, the first 2 modes will be in this dual rail encoded state. So after that step, we can actually just sort of apply the KLM theorem sort of in its black box form and do everything that they're doing. And then at the end of the computation, we can apply a decoding gadget to reset the state back to the all 1 state. And this is actually the sort of entirety of the proof now. We've started in the all 1 state. We applied this encoding gadget to get the dual rail encoding, in which we can use the KLM theorem, and then we sort of decode at the end. So once again, sort of just putting this all together, right, we had this quantity delta C over 2 to the n, which is equal to this transition amplitude in the quantum circuit. We just showed how to convert that quantum circuit Q into this linear optical circuit, where now we have one photon in every single mode and ending in one photon in every single mode. Now we have this like much grosser factor out front here, but like, so is life. You just have to deal with it. But the upshot is that this transitioning amplitude here, as we sort of carefully prepared, is exactly equal to the permanent of L, right? And because L is the unitary matrix, now we've shown that if you can calculate this permanent of L, then you can sort of work your way back to calculate this quantity delta C, which is the Sharpie hard quantity we wanted to compute in the first place. So that sort of completes the proof of the unitary case. Something you might ask is, well, how does one actually find these gadgets? Like, how do you do this encoding and decoding and so on? Well, it's sort of like embarrassingly simple. What you do is you guess the transformation that you want to have. You have these various constraints that you need, and then you just use a constraint solver. Now, there's like a little bit of black magic involved in like getting the constraint solver to give you a solution which kind of looks nice. But if you sort of mess around with it, you can sort of get it, and it'll spit out a matrix like this, which is the encoding matrix that we use to take one photon in the first mode and dump it into the third mode. So that's how you find these gadgets. And then so how do you take a theorem like I just described to you, which shows that the permanent is hard for unitary matrices, and convert it into a theorem about finite fields, right? Because this is sort of Yeah,
sure. Daniel, can I just ask the question on the previous slide?
Yeah.
If you just go back one slide.
Sure thing.
Yeah. So there, I guess your proof is relying on the fact that this encoding is reversible, and so the permanent of phi wedged between this encoding is, it's a unitary state.
The encoding is actually not reversible because when you're using post-selection, like reversibility just sort of goes out the door. Like things are really gross. But it just so happens that there's a different gadget that you can use both times. There's a gadget that you use for encoding, and there's also a gadget that you use for decoding. And both of them together sort of give you what you want. But it just because you have the encoding or the decoding gadget doesn't mean the other one exists.
Right. Okay. Thanks.
Cool. Right. So so how do you get this theorem about finite fields? It's actually, once again, it's very conceptually easy. You just sort of inspect all of the gadgets that you used during your construction, and you just sort of notice that all of these gadgets, all of the entries lie in this field Q adjoint alpha, where alpha is this thing. So then you just sort of need to exhibit a field, finite field in which these square roots exist. And then you sort of apply some, standard number theoretic techniques. So I'm getting very close to the end of my time here. So I want to briefly mention permanent approximation. So everything that I mentioned in this talk was about computing permanence exactly. But it turns out that for multiplicatively approximating the permanent, still a lot is known. In fact, even as soon as Valiant published his initial work, it was also noticed that multiplicatively approximating the permanent is still Sharpie hard. And the argument goes something, I'm running a little low on time here, but the argument is roughly like you sort of perturb one of the entries of the permanent and use that to sort of binary search to what the permanent actually is. In fact, you don't even need a multiplicative approximation to do these things. You just need to know what the sign of the permanent is. And if you know the sign of the permanent, you can use binary search to find what the permanent is exactly. The problem with these sorts of reductions is that they don't preserve orthogonality, but there's sort of a simple fix, which is just to binary search on this quantity delta C directly by just sort of artificially increasing and decreasing number of satisfying solutions in your circuit. And so a corollary of this idea is that any multiplicative approximation to the permanent of an orthogonal matrix is still Sharpie hard to compute. And so I just want to conclude with sort of a description of the landscape of permanent complexity here. So the first result we saw was that, computing the permanent of a arbitrary complex matrix is Sharpie hard by Valiant's theorem. And then we just saw that computing it, giving a multiplicative approximation is still Sharpie hard. And same thing goes for orthogonal matrices, which we described earlier in this talk. And in fact, earlier I also mentioned that even computing the permanent of a 0-1 valued matrix is Sharpie hard to compute exactly. But probably a lot of you know the punchline here, which is that if you want to multiplicatively approximate the permanent of a non-negative matrix, then there's actually sort of like a beautiful polynomial time approximation scheme which will do this. And so the final class of matrices that I want to bring up are the positive semi-definite matrices. So we actually also handle these matrices in this paper, albeit with like a completely different technique using some sort of standard polynomial interpolation arguments. But in fact, computing the permanent of a PSD matrix is still sharply hard to compute exactly. But multiplicatively approximating, we don't know. And it's sort of a really interesting open question. We believe that it's not sharply hard, but we don't know what the exact complexity is. So I'll end there. Thanks.
Thanks, Daniel, for a fascinating talk. So we'll take any questions that people have at this point. We have 8 minutes for questions. Maybe I can get us started. Daniel, on this question of approximating the permanent of a positive semi-definite matrix, maybe this is putting you on the spot a little bit, but there was a paper by Barvanok like yesterday or 2 days ago on this topic.
Oh,
did you see that?
I don't know. I did not see this.
Okay, so he claims a multiplicative approximation scheme for the relative error case in the case where the permanent is between 1 and 2, I think. Like you need to have some bounds on the entries, I think. And he has some range of permanents that can be computed efficiently. But anyways.
Okay, that sounds very, very promising. Yeah, I have not seen the results. So the best result that I knew sort of prior to this was this deterministic algorithm given by Amin Saveri and some other people, which is a deterministic approximation algorithm. But the approximation is really terrible. It runs in polynomial time, but it's exponentially bad. So.
Thanks. So if anyone has any other questions, we'll wait for a minute or two.
Maybe a comment. I think that AGGS, so is one of the G's Gervitz?
It is Gervitz, yes.
So he actually presented this result in a Tutte Colloquiua maybe 2 years ago. And I think he prefaced it by saying, I'm about to present the result I hoped I might prove before I die. You might remember, he said, he says these sorts of things. But so it might be hard to extend.
Yeah, so I've heard from other people that he thinks that it's tight. I personally do not hold the same opinion. But
wait, Daniel, are you one of the other G's on that paper?
No, I'm not. I'm not one of the other
okay.
G's. Okay. It's a bunch of people at Stanford plus Gervitz.
Okay.
So maybe I have another question. So is anything known about the hardness of approximating permanence over number fields? That's sort of an intermediate case, right? Because you know that like doing it over the complexes should be at least as hard as doing it over, say, finite fields. Like for instance, do your results imply any hardness results for specific fields? Like, I don't know, Q root 6 or something like that?
Are you talking about orthogonal matrices specifically, or just any class of matrices?
Say any type of matrix group, but just take the points over a number field, not over the reals or the complexes. That's like an intermediate case that could be easier or hard in a given situation.
Well, I mean, even if it's just a 0-1 matrix, it's still sharply hard to compute.
Possibly, yeah.
Well, I mean, this is just true.
No, I see.
Okay.
I had a question. I was just wondering, because you mentioned also, well, you said that the technique used for the positive semi-definite matrices was different, but what about you mentioned a few other classes like general linear and symplectic matrices. I was just wondering, like, if you could, like, real quick say, like, is that the same technique, or?
Yeah, those are all the same techniques. In fact, I mean, you know, like orthogonal matrices are invertible, so you just get that result for free. I mean, we have some sort of like, we try to be like absurd as we can in our paper at some point. Like, we can prove that like real orthogonal symplectic involutions promise that the permanent is positive. Like, if you take all of those conditions together, then that's still sharply hard to compute.
Okay, so you sort of attack them all at once. I guess I see how, like, with the orthogonal group, that would be taken care of by the unitary, but just for like the symplectic group, say, I don't really see.
Yeah, so it's not taken care of automatically, but there are some very simple reductions that you can do to sort of to get what you want. Like there's like this some standard trick where you like put the the matrix that you want like along the off diagonal, and the permanent is just like the square of the things, and this just works.
Yeah. Okay. Thanks.
Sorry, Daniel, I have a potentially stupid question. It's been a little while since I've thought about these things, but I thought the permanent was so like if the permanent was Sharpe, well, because of the Stockmeyer algorithm, you should be able to multiplicatively estimate Sharpe complete quantities in the third level of the polynomial hierarchy, right? Is that correct?
Sorry. Can you phased out for a second? Can you repeat the question?
I was saying that because of the Stockmeyer algorithm, you should be able to produce multiplicative precision estimates to Sharpe complete quantities in the third level of the polynomial hierarchy.
Yeah. So there's this like really unpleasant sort of technicality here where these problems are sort of like technically in gap P, like they're both,
right, yes.
They deal with both positive and negative numbers. And in these classes, that's not true. You can't do the Stockmeyer approximate counting thing.
Right, thanks.
I have maybe a less stupid question than my last one. So what about a finitely generated group of matrices? Let's say you have some matrices over the rationals or a number field. Is anything known about that case? So these would be what people call arithmetic groups, or they're closely related.
That I'm not sure about.
I might expect nothing's known, but I'm just curious.
Yeah, I don't know anything off the top of my head about that. Sorry.
Okay. So if there are no further questions, then let's thank Daniel, and that will conclude the TUT seminar portion, and then we'll move on to the virtual grad house.